Hi everyone, thank you so much for joining us for today's low voltage motor testing webinar. I am Meredith Kenton, the digital marketing specialist here at Megger. If you have any questions about webinars in general, feel free to reach out to me. If you have questions during this presentation, I invite you to submit your questions on the panel on the right-hand side of your screen. It should look just like this one. At the end of the presentation, I will read the questions out loud to Jose and we'll get through as many as we can. If your question isn't answered, it will be answered following the presentation via email, so don't worry about that. And on that note, I will hand it over to Jose, our presenter today.
Hi, good morning. Thank you, Meredith. Hi, everyone. Let me introduce myself. I'm Jose Miguel Zambrano. I'm application engineer to Megger CSA. I'm an electrical engineer. I had a master in operation management. I have 17 years of experience in position related to electrical predictive maintenance. I've been working in pulp and paper, oil and gas, metalworking, food and beverage, and other segments such as mining, steel, and marine. Currently, I'm in the Megger Baker Instruments since August last year, and like I said, I'm an application engineer for CSA and Mexico. Well, again, good morning with all. It is a real pleasure for me to be here with you today, sharing all this knowledge on this important topic. Today, we're going to talk about low voltage static test for electric motor. Basically, we're going to deal with the point described in the webinar outline, as you can see over there. First of all, we'll define the static test, and then we'll see 7 static tests that allow us to verify the condition of the motor insulation system. We're going to talk about temperature measurement and how this variable affects the insulation system test. Also, we're going to see why we have to use the voltmeter and verify the phase frequency, and how that verification helps us to know the motor rotation. And then we're going to talk about a little bit about the continuity and diode test, and finish with the Kelvin method and the inductance and capacitance readings. At the end, we'll check bullet points that resume the importance of this test. All right, let's begin. Let's see then what are the static tests and how they are performed. Let's start by giving a concept to a static test and to know what are they. What do they tell me? These tests are carried out to establish the state of the motor insulation system when the motor is de-energized and, if it is possible, disconnected. This test must be done in the motor junction box. However, we know this is not always possible. So in the cases we have to go and do it from the MCS, but if a fault is detected by carrying out the test from the MCC, the problem could be either on the motor or in the power cable insulation. So we have to be very sure about the fault's location and how it's going to affect the whole system. The static tests are divided in 2 groups: the low voltage test and the high voltage test. In this webinar, we go to see in detail with the low voltage test. These tests are performed at or below the bus voltage, never above that level. However, in order to have an effective diagnosis of the insulation system, they both must be performed. Low voltage tests are pass or fail tests, but the high voltage tests are the tests that give predictive indication and allow me to have a clear scenario of the motor insulation condition, as we see a little on. Now, let's take a look at the degradation graph. What we can see here is the insulation behavior versus time. It is very important that we clearly understand this graph. Here we can see how the insulation system is degraded in an electric motor. No matter how big or small the motor is, doesn't matter its design, its power, or its type. All electric motors show this behavior when aging their insulation. Also, it's evident when the motor is new, its insulation system is optimal. It is the best possible, and therefore its breakdown voltage is high. But as time goes by, due to the effect of the temperature, contamination, humidity, and mechanical condition, such as imbalance and misalignment, the insulation system is degrading until it intersects with the bus voltage. In this point, when the two curves intersect, the motor failures occurs. Now, as we said before, the low voltage tests are made at or below the nameplate voltage. So these tests verify the state of the insulation in this area. However, these tests tell me only if the motor is located above or below the short circuit point, but they don't tell me in which area of the curve the motor is located. That is why they are defined as pass or fail tests. In the same way, we can observe that the motor does not always see the bus voltage in operation, but they are voltage peaks that are generated by starts and stops and other operating conditions such as load or speed changes. In order to know at what point of the curve the motor is located, it is necessary to do high voltage tests. Since this test identify whether the motor is in the high zone insulation, the low insulation zone, or the arc zone. Let me point here in the presentation where are these zones. Over here we have the high insulation zone. Over here we have the low insulation zone. This is the arc zone and this is the short zone. So the high voltage test identify whether the motor is in the high insulation zone, the low insulation zone, or in the arc zone. So you may wonder, if the high voltage tests are the ones to give the most information, why should I perform the low voltage test? And the answer is very simple, because the EISA AR100 standard indicates that the high voltage test can only be performed in a predictive focus, of course, as long as the motor has passed the low voltage test. So at the end of the day, if we understand this graph, we will understand the structural basis of the electric motor static test. Okay, now let's start by talking about temperature measurement. As we all know, and you are here because you have a predictive maintenance focus, any predictive technique is based in two fundamental aspects. First of all, must have a database that provides a trend. Secondly, that the measurements in that database are made under the same condition. Therefore, the IEEE 43 standard establishes that regardless of the winding temperature when the measurement was made, all the insulation resistance measurement must be corrected and referred to 40 degrees Celsius in order to have a reference for the measurement comparison. That's why the temperature measurement is so critical for the insulation resistance test. We can use several equipment for this purpose. We can use a T, J, or K thermocouples, laser thermometers, or thermographic camera, wherever you want. But we have to measure the temperature. It is a very critical variable of the system. Now, once the motor temperature is measured, It is necessary to have an equipment that can do the mathematical calculation and make the measurement correction, according with the IEEE 43 standard. After making this calculation, it is possible to do a measurement comparison. It doesn't matter if the winding temperature is above or below 40 degrees Celsius in the moment of the test. The important things to make is the corresponding correction. We can't forget that. The KT factor that you can see in the graph is the number by which the measured value must be multiplied to make the correction. Now, let me give you some temperature tips. When the motor is heated in an oven or by any external means, such as, I don't know, lamps, for example, the winding temperature will be very similar to the motor casing temperature. But if the motor has been running, and of course it is hot, and we measure the temperature in the motor casing, the winding temperature will be that reading plus 10 degrees Celsius approx. This is not in the standard. This is just a rule of thumb. Okay, now let's take a look at the most famous and performance static test of all, the insulation resistance test. When we talk about the insulation resistance measurement, all the equipment that does it relies in one important law to deliver the resistance value, and that is the Ohm's law. This is defined as the relationship that exists between the inject voltage and the current measured. However, it is necessary to understand the behavior of the current when the motor is supplied with a DC voltage. And precisely that is what we're going to see in the following slides. Because immediately after we start supplying the motor with a DC voltage, 4 currents appear in the motor insulation. These 4 currents are the following: capacitive current, or you can name it charging current too. Second, absorption current or polarization current. Third, conduction current. And 4, leakage current. The total current will be the sum of those 4 currents. Now, knowing this, let's take a look at the electrical behavior of each of one of them. Well, here we have a graphic representation of an electric motor insulation, where we have the winding represented by a copper conductive plate, the casing that in this case is our ground reference, and the material between them that we define as insulation. Into the insulation material, we can see a lot of dipoles and free electrons. Now, when we supply the motor with the AC voltage, those dipoles and electrons will be changing their position depending on the value of the signal, if it is positive or negative. So the dipoles and the electrons will be in constant movement. Now, let's apply a DC voltage and see how it affects the electrical circuit. When we supply the motor with the DC voltage, the behavior is completely different, and we can see how immediately after applying the voltage, the first things that happen is that the free electron present in the insulation now move quickly towards our positive pole, in this case, the winding. This behavior is the free electrons. In the free electron is defined as the capacitive current or the charge current. This current has a very high value at the beginning, but once we reach the voltage test, it is quickly discharged. Then we see here in the presentation, we see how in presence of DC voltage, the dipoles present in the insulation begin to align themselves little by little thanks to the new magnetic field. This dipole behavior is defined as absorption current or polarization current. This current also has a high value at the beginning, but not as high as the capacitive current. It also discharges, but takes a long time than capacitive current to do it. Then we have the conduction current. This current is very small, but it is present and it is constant over time. It doesn't discharge, and it depends exclusively on the modern insulation material. And finally, we have the leakage current. This current is the one that circulates through the contamination of the insulation and increases as the insulation is more degraded or aged. At the end of the day, this is the current that we are interested in measuring in order to calculate the insulation resistance. Since this current is indicative of the modern insulation system condition, the main characteristic of this current is that it is constant over time. It will not vary as a time function. So, after a certain period of time, and taking into account the behavior of the other currents, the leakage current will be the only relevant in the circuit. Okay, now let's see how these four currents interact with each other and how we should do the insulation resistance test in order to be sure that we are making the measurement with the important current, the one that interests us, and that is the leakage current. Taking into account that the total current is the sum of the four that we saw previously, when adding the capacitive and the absorption current, we have a result like one shown in the animation, where the high initial value of both currents is evident, and also how they discharge over time. They both have a very high value, and with time, over time, they are discharged to ground. Okay. Now, let's add the conduction current. This current is constant, but very small. So it will add a very small value to the total, as we can see in the animation. And finally, we can add the last current, or the leakage current, which, as we know, is the current that will circulate through the contamination and or the degraded insulation. And because it is constant over time, at the end, we will have a behavior like the one shown in the presentation. Therefore, if we wait long enough, only the leakage current will be present in the measurement. That is why the IEEE 43 standard establishes when the insulation resistance test is carried out, the measurement must be made after 60 seconds of reaching the test voltage to allow the discharge of the current that we are not interested in, to avoid that they affect the measurement. Here you can see this is the figure shown in the IEEE 43 standard and show us the behavior over time of the four currents. This occurs each time a motor is supplied with a DC voltage. Each time that we supply a motor with a DC voltage, this is the behavior that we can see in the installation. Okay. Now, what are the recommended voltage for the insulation resistance test? At what voltage level should the insulation resistance test be performed? In the IEEE 43 standard, it is indicated by the following table. what is the value of the voltage that must be applied in DC depending on the nameplate voltage. As you can see, for each level of bus voltage, there is a range of voltage that can be used to perform the test. Let's take an example. For example, in 480 volt motors, according to the table, the test has to be done at 500 volts. If we take the case of a 4000 volts motor, the range will be between 1000 and 2500 volts. We must note this standard is valid only if the OEM doesn't indicate us the voltage level we must reach in the test. But if in the manual or a user guide, the OEM clearly establishes the voltage level of the test, this should be taken as true, and the IEEE 43 standard should not be considered. There are cases when motor OEMs indicate that the insulation resistance test must be carried out at nameplate voltage. If it is a 4000 motor, then the test must be carried out at that voltage and not the one established in the standard. So the message here is the IEEE 43 standard will never be above the OEM instruction. The recommended values in the standard must be considered when we don't have any type of information or indication from the manufacturer. Now, after performing the test, how do we know the motor passed the test? What are the minimum values established in the standard for insulation resistance? The answers are in the following table, where we can see three motor categories that must be taken into account to define whether or not the motor passed the insulation test. It must be very clear that the values established in that table are those corrected to 40 degrees Celsius. They are not the values measured directly for the motor. So we have three categories here. The first, the winding made before 1970. For those motors, the minimum insulation resistance value is given by the mathematical expression that you can see in the table. kV plus 1. You have to go to the nameplate voltage, convert it to the kV, and put it into the formula, and you have the minimal value for the insulation resistance for that motor. If the motor or the winding is built after 1917, so the minimal insulation resistance value is 100. For the most machine with random wound or rated below 1 kV, the minimal insulation resistance value is 5. But once again, if the OEM tells you what the minimum insulation resistance value should be, and it is not the same or not even close to those seen in this table, you have to take into account what is indicated by the manufacturer. Let's now go on the PI or DA test. In this test, we are checking the ability of the insulation to polarize, to make sure that each insulation dipole can align correctly with the field. This is only possible if the insulation material is not dry, cracked, contaminated, or wet. Now, how do we know if we are going to perform the PI or the DA test? The IEEE 43 standard establishes that if the insulation resistance measured in 1 minute is greater than 5,000 megohms or 5 gigaohms, then we must do the DA test. If it is less than 5,000 megohms, then we must perform the PI test, no matter the motor size. And what are the formulas to do the calculation? As you can see in the slide, the PI formula is the insulation resistant value at 10 minutes divided by insulation resistant value at 1 minute. For the DA calculation, in the standard, two examples are established. It can be the insulation resistant value at 1 minute divided by the value in 30 seconds, or the value at 5 minutes divided by the value in 1 minute. However, the standard indicates that these formulas do not limit other ways of calculating. Now, what are the minimum values established in the standard to pass the PI test? The table shows, according with the motor insulation class, which are the minimum values for the PI. We can see if we have a motor with an insulation class A, the minimum PI value is 1.5. For the other types of insulation, the minimum value for PI is 2. Okay, now let's talk about an extremely important aspect. Can I repeat the PI test? The test can be repeated as long as the windings are fully discharged to ground. The IEEE 43 standard states that to ensure that the windings are completely discharged, they must be grounded for 2 hours or 4 times the test duration. Once this procedure is done, then it is possible to repeat the PI test. If we repeat the test without having discharged the winding, it will give us a wrong value because it is not possible to polarize a material that is already polarized. Although the standard established limit of 1.5 and 2 for the PI, when we get in the field values greater than 1, it is common practice like the motor work, because it means the insulation was able to be slightly polarized. In the standard, there is no table of minimum value for the DA. However, it is assumed that the DA limits must be very similar to those of the PI. Okay. Now, why do we have to use the voltmeter? Why it is important? Well, one of the most important aspects to take into account regarding the motor operation is the voltage level of the power supply. That is why the supply voltage must be measured before starting a motor. The NEMA MG1 standard establishes the limits for both, for overvoltage and low voltage in the motor power supply, as well as for voltage imbalance. These aspects must be frequently monitored to avoid damage to the motor when it is in operation. This variation is in the power supply in the most of the time make the motor operating too hot. According to the OEMs, the motor are designed to work with plus minus 10% of the nameplate voltage. And the standard indicates that deviation in the voltage supplies should be always less than plus minus 2%. We have to know that the variation in the voltage produces changes in the motor performance. The voltage is the most important variable in the power supply of the motor. We have to take into account that we have to measure the voltage frequently in order to be sure that these values are within the limits established in the NEMA MG1. Okay, what happens if we have problems in the power supply, in the voltage supply? Here we can observe the consequences in the motor when it works with over or low voltage. Think about it. A steady state, three-phase system. There can be only three things that are wrong with your voltage condition. First, the level. Second, the balance. And third, the distortion. Typically, you will have a combo of those with different grades of severity. Very important to have in mind. Pretty much all voltage issues come from upstream. And whatever problem you have with the voltage bus, it will affect the whole voltage bus. It is not only the one motor that you are testing that is in trouble. It is all the motor connected to that bus. Thinking about all the role of MCC at which you are standing, at minimum. Walk upstream and find what causes the problem and fix it. If you can't, make sure that all of your critical motors are derated properly so they are not running too hot. There is one exception. It is when we are working with VFDs. The VFDs create their own voltage condition downstream. Whatever happens downstream of the VFD is not caused by what is happening upstream of it. Think of the VFD as creating 100% of the voltage condition downstream. Okay, before connecting the motor, we must identify the phase sequence of the power supply to make sure that the motor is going to rotate in the direction that the load requires. If the rotation of the supply doesn't match with the motor rotation, the load equipment that is connected to the motor shaft, whatever it was, will not operate properly. For example, if we have fans, we have to do this verification because it's very important for the functioning of the fans. The same with the pumps, with lift, with elevator. So this is a very critical issue for some of our applications. So it is very important to know what is the sequence of phase in our application. The motor rotation is establishing, the motor rotation is very important because it ensures the proper functioning of the load. This aspect goes hand in hand with identifying the phase sequence and the power supply. Both must match depending on the direction of the rotation required by the load. How do we define the direction of rotation? And this is very important. Well, the standard EN 634-8 help us clarify doubts and define the direction of rotation depending on the system configuration, as we can see here. The direction of rotation must be established on the coupled side of the motor. So the first things we have to do is identify the coupling side of the motor. The coupling side is the side where the motor shaft extension exists. For motors that have shaft extension in both sides, the coupling side will be either the end with the largest shaft diameter or the ends that have this, if the ends have the same diameter, the opposite side to where the fan is located. So we have to follow this instruction to know where is the coupled side. And then with the coupled side defined, we can decide if the motor is going to rotate clockwise or anti-clockwise. In the end, we have to know which is the coupling side of the motor in order to determine the clockwise or anti-clockwise rotation of the motor. Continuity measurement and diode test. The continuity measurement allows to measure the resistance value between 2 points. However, through this method, both the resistance between the 2 points and the resistance of the cable used are being measured and affecting the readings. Therefore, there must be taken into account certain aspects to try to make the measurement as accurate as possible. The first things that we have to do is the resistance of the lead must be override. This is the first things to do. And we have to take into account that the contact resistance will probably be different for each measurement. Therefore, a small difference in the resistance can be expected for each reading. So, this procedure is recommended when the resistance value to be measured is in the order of ohms, case that usually occurs in small electric motors. This method is generally used to measure phase measurement, a single coil, and it's recommended, as we just said, to measure the resistance of the winding in small motors. If we need to do a measurement in the large motor with big winding, we have to do it with other method like Kelvin method. What we can find? We know that the cable resistance is directly proportional to the length and inversely proportional to the diameter. So variation in the winding turns will result in variation in the motor resistor imbalance. Hence, we can detect the following problem. Different number of turns per phase. If we have different number of turns, we will have a different length per phase and therefore variation in the resistance. We can also find a different copper diameter, high resistance connections, total shorts between turns, opening winding, and of course, and the most important and critical issue, we have to build trends, because with the trends, we are able to avoid the catastrophic failure. Now, what are the maximum values for the resistive imbalance in an electric motor? According with the IEEE 1415, if the motor is brand new, we shouldn't have more than 1% of resistive imbalance. If the motor is repaired, and that is coming from the repair shop, the limit is 3%. And if we are talking about a motor in use, the limit is up to 5%. The important thing here is to be able to build trends with the different measurement so we can anticipate the catastrophic failure. Diode test. Okay, the diode test measures the voltage in both directions, in both sides of the diode, because as we know, diodes only conduct electricity in one direction. So having the voltage reading in both directions, we can detect any damage to this device. If we do the test, how do we know that the diode is working like it should? So if the diode is in good condition, when I do the test, I will read 0.6 volts in one direction and open circuit in the other. If our diode is shorted, then the reading will be 0 volts in both directions. If we have an open diode, it will show open circuit in both directions. The diode, they are not very common in the motor application. They can be found in some alternators and in the polarity control of extension circuit. But it's good to have the ability to measure this electric equipment. Let's talk about now the Kelvin method. When we're talking about very small resistance measurement, we can't use the continuity measurement method. We must use a much more precise method to be able to perform the test. For these cases, the Kelvin method, or also called the 4-wire method, is used. Through this circuit configuration, the measurement eliminates the error to the cable and the contact resistance, making the measurement much more accurate. For large motor, where the winding diameter conductors are much larger, this is the method that should be used since we are talking about values around milliohms. This test can be performed unidirectional or bidirectional. This is recommended when the connections are made through different materials. Let's take a look of the thermal effect or the Seebeck effect. What do we mean when we talk about bidirectional? We do this measurement when we want to eliminate the Seebeck or the thermoelectric effect. The Seebeck effect is a phenomenon in which a temperature difference between two dissimilar electrical conductors or semiconductors produces a voltage difference between the two substances. If we measure in only one direction, a voltage will be generated and can alter the measurement. But if we do it in both directions, we can eliminate the effect and the reading will be as accurate as possible. Inductance and capacitance. Let's see. Here we can see an extract from the standard for these two variables. The IEEE 1415 standard states that although they can deliver a large amount of information, they are only useful if we build a trend analysis. And I have to emphasize this aspect, only by trend. If we make a single measurement of inductance and capacitance, this value doesn't indicate the insulation shifting condition. Only through an inductance and capacitance trend can we make an accurate analysis of the motor insulation condition. What can inductance measurement tell us? This variable is very useful because, as you can see in its mathematical definition, the inductance depends on the square of the number of turns. Instead, the resistance is linearly proportional to the length. That is why any change in the structure of the winding insulation system will have a greater effect on inductance than resistance. Now, what we can detect with this test? First of all, we can detect inverted coils. Second, eccentricity, change in the air gap, because the rotor electromagnetic influence on the stator. And here is a very important aspect, short coils, between coils or between phases. But I have a very important things to say here. This test, the inductance test, does not detect weak insulation between turns. It only can be made through the source test. So we can detect shorts with the inductance test, but if we want to be predictive and be ahead of the failure, we have to do the source test. Also, we can see rotor porosity or broken bars. Capacitance. As we said before, capacitance is useful, like inductance, only by trend. That is why we must take several measurements before carrying out any kind of analysis. Now, let's see what can we know with the capacitance test. We have here two scenarios. If we detect an increase in the capacitance to ground, this is associated with increased pollution, high humidity, insulation breakdown, or insulation delamination. But on the other hand, a decrease in the capacitance to ground may indicate aging of the insulation. Again, the important things here is, as we know, electric motors have a big inductive effect. Therefore, their capacitive effect is very small. So the equipment used to measure capacitance must be able to read very low values, because in motors, capacitance is generally less than 100 nanofarads. These two variables, the inductance and the capacitance, always are useful if we build a trend. With the trend, we can take decision. Only one measure don't tell me anything about my insulation system. Okay. Now we're going to make a quick summary of all the tests, highlighting the relevant points of each one. The first, temperature measurement. The temperature measurement, as we saw, is critical aspect to determine the electric motor insulation system condition. It's the first things we must know before doing the insulation resistance test. We have to measure the temperature. It's very important. If we do not do that, we can compare our measurements. We have to measure the temperature in order to do the correction when we perform the insulation resistance test. After performing the insulation resistance test at the voltage level suggested by the standard, we must make the correction of the resistance value at 40 degrees Celsius and compare them with the limit established in the standard. This is only in the case the manufacturer doesn't tell otherwise. We must measure the motor power supply voltage level to ensure that they are between the limits established in the standard, in the NEMA MG1, and prevent the motor from running overheating. The definition of the phase sequences help us determine the motor rotation and therefore ensure the load proper function. We must perform the continuity test when the resistance measurement is in ohms. That is, for example, in small motors, and when we need a very accurate measurement in milliohm, for example, in large motor, we need to use the Kelvin method. The inductance and capacitance test are only effective by trend. A single measurement of this variable is not enough to define the insulation system condition. So, finally, what does Megger offer? What is the option that we present to the market? Normally, the clients, you guys, need one equipment to perform each of these static low voltage tests. In the base of the cases, you have one equipment that does 2 or 3 of these tests. Megger offers you one hardware only with the ability to perform the entire set of the tests described in this webinar. And that hardware is the MTR 105. Now, what are the MTR benefits? In the first place, the equipment use rechargeable batteries. So you don't have to buy batteries frequently. It uses rechargeable batteries. Second, it has a very intuitive controls. It is very, very easy to use. Very important point. This equipment can perform the insulation resistant temperature correction. So you don't have to worry about when you do the measurement. You always going to have the correction of the value in the insulation resistant test. It operates up to 3,000 meters above the sea level. It is very light and portable. It can handle a database of up to 256 motors, so you can have all this information in the equipment, and you can download it to your PC through the USB flash drive. And this is maybe the most important thing. You're going to have only one single instrument to calibrate. You don't have to send to calibrate 4, 5, 7, whatever number of equipment you have. You just have to calibrate one and only one equipment. One single instrument to load, and because it's very light, it's a great benefit. And of course, one single instrument to connect and test in the model. So at the end of the day, we face 7 equipment in just one. All these tests that we are talking about in this webinar, the MTR 105 can do it. Well, thank you. Thank you very much. We have reached to the end of the webinar. It was the information that I wanted to share with you today. Now we will answer some of the questions that you may have. So, Meredith,
Yes.
whenever
Hi,
you want.
Jose. Okay, so the first question is, would you test a 690 volt AC motor with 500 or 1000 volt DC? Is there an explanation on why low voltage motors are tested with voltages over its nominal value, but in high voltage motors, the IEEE asks to use less than nominal voltages for testing?
Yes. Let me go to the table to show. Yeah, here we are. So no matter, doesn't matter what is the winding rated voltage. If it is under 1000 volts, you have to do the insulation resistance test at 500 volts. If it is 200, 400, 600, it doesn't matter. You have to do the insulation resistance test at 500 volts. Now, above 1000 volts, we don't have a single number. We have a range. So you can select any value within that range. Okay, you can select the minor value or the maximum value or the average value. It's up to you. The important thing is that the value that you choose is within this range. Why the test voltage for motor above the 1000 voltage are below the nameplate voltage, and that is because we don't have to stress the winding too much. So that is why the numbers are below of the nameplate voltage.
Okay. The next question is, if capacitance increases with increasing applied DC voltage, what does this indicate?
All right. We say that one of the more important things to do a predictive technique is do the measurement under the same condition. Okay, we have to do the measurement always in the same condition in order to be able to compare the measurement. So it really doesn't matter that obviously there is a limit, but the equipment do the capacitance test at the voltage that is fixed in the equipment, so we can compare the measurement in the future. If we do the measurement with a bigger value of voltage, obviously the capacitance test reading is going to change.
Okay, the next one, okay, this is a little bit longer, but is it standard that when the system phase sequence 1, 2, 3, and phase 1 is connected to lead T1, phase 2 is connected to lead T2, and phase 3 is connected to lead T3, that the motor will rotate in the clockwise direction when facing the shaft as you have described?
I'm sorry, Meredith. The communication is something wrong. Can you please repeat the question, please?
Yeah. Okay. So they're asking, is it standard that when the system phase sequence is 1, 2, 3, and phase 1 is connected to lead T1, and phase 2 is connected to lead T2, and phase 3 is connected to lead T3, that the motor will rotate in the clockwise direction when facing the shaft?
All right. Yes. When we have what we call the positive sequence, and we do the procedure in the standard in positive sequence, we are going to have a clockwise rotation. Yes, that is right.
Okay, the next question. Does the information presented apply to DC motors as well, or are there different test methods for DC motors?
Okay, for the field winding, the limits are exactly the same. Okay, but when we are going to test the armature circuit, that is a little bit different. So we have to take some extra cares in order to do the test in the armature circuit. It is a little bit different.
Okay, the next question. What was the temperature addition rule of thumb? It was add 10 degrees Celsius when?
Oh, okay. Um, when we are going to do the insulation resistance test, and we are just uh, uh, stopped the motor. It was running in their application, and we stopped, and we're going to do the insulation resistance test. The motor is obviously is hot, you know, and we don't have access to the winding. We do the temperature measurement in the case of the motor. So we are doing the measure of the temperature in the case of the motor, but that is not the temperature of the winding. So if the motor was running, we have to take the reading of the temperature in the casing of the motor, and we have to sum about 10 degrees Celsius in order to know what is the real temperature of the wine. But as we said in the webinar, that is not in the standard. That is just a common practice, a rule of thumb.
Okay, and the next one's also about the rule of thumb. Does the rule of thumb, does the rule of thumb of temperature, casing, and winding temp have a difference of 10 degrees Celsius apply for single and three-phase too?
No, no, no. It's the same. It's the same. As long as the motor was running, that is the number that we add to the temperature reading in the case of the motor.
Okay. The next question. What is the diode test used for?
Oh, okay. When you let's see, when you have, for example, rectification bridge, you need to know with certainty that all the diodes in the configuration of the circuit are working fine, you know, because otherwise the outcome will be whatever. So in some very specific application, you have to know how the diode are working. So I know in the motor, there's no so common to see diodes working with the motor, but it's very useful when you have a electronic circuit over there doing something on the motor, and you have to be sure that it's working like it should.
Okay, the next question, what makes leakage current for the motors?
Okay, the leakage current is the current that escape, if we want to use that word, is the current that escape through the insulation. The leakage current can go through the insulation, or can go through the contamination, or can go through both of them. So when you measure the leakage current, you are doing analysis of the condition of the insulation and or the contamination in the motor. That is why it's very important to focus only in that current, because it delivers information about the insulation condition and probably the contamination condition in the motor.
Okay, I think we have time for two more. The MTR 105 does a three-phase insulation test for each phase winding as an automated sequence test. Why was a fourth connection not provided to carry out phase to earth as part of that test sequence?
Okay, this equipment can do very particular test. Let's see. We can do a insulation resistant test face to ground. We can do a resistant insulation resistant test between faces, between two faces, and we can do the insulation resistant test between the three faces, and also we can do the measurement with a guard cable, and that is an option that we have to eliminate the contamination readings and only be focused in the leakage current that is going through the insulation. So depending on what do you want, you can connect the cable as you want it to do the test and know if you want to do a very particular test.
Okay, and then the last question, sorry, let me back to it. For a polarization index test, is there benefit in recording extra data to show the curve over 10 minutes? And why does the MTR 105 not record this if there is a benefit?
Let's see. I think maybe for more than 10 minutes, in 10 minutes, the standard established that in 10 minutes, the insulation is going to be as polarized as it can be. So if you extend the time of the test, maybe you don't get anything more because the value in that point in 10 minutes, it's going to be constant over time. So maybe in very, very large motor, you can see extra information because we have so much material, so much mass. So maybe we have to do a little more time to polarize all the mass, but in the most of the motor, 10 minutes is enough to know what is the PI value. So that's it, Meredith. Thank you very much.
Thank you, everyone.
Thank you.